Hello class, this is Dr. Ben. Good day to you. And here is another problem out of the middle part of chapter 4 that has to do with the combination of force and motion concepts. So we look over this problem about Batman pushing off against the ground, and so this problem is occurring in a vertical direction. And if we read the problem carefully, we see that we really need to consider this problem in two different parts. Because there's a part where Batman is pushing off against the ground, and then there's another part where he's going upwards through the air, eventually to rest before he comes back down. And those two parts of the problem have different accelerations. The flight part has to do with gravity, and the launch part has to do with him pushing off of the ground. So it looks like this problem gives us a lot of information about the motion of Batman. So I believe that this is going to be a motion first problem that we use basically to find the acceleration of Batman during the time when he's in contact with the ground. And then we can transition to the forces second, and we can use that acceleration in order to find this pushing force, which seems to be the goal of the problem. All right, so since the motion part of the problem has two parts, we need to carefully draw a pictorial representation for that situation. So let's put it on a vertical axis, and we're going to have three different points of interest. So we're going to have the position of Batman's center of mass at the beginning of the experiment, and then when the feet leave the ground will be the location of the center of mass will be another point, and then when Batman's center of mass gets all the way to the top of the trajectory. So let's label these points 1 and 2 and 3. So we'll put the origin at point 1 and call the positive y direction upwards. So we'll have the kinematic variables y1, v1, and t1, and then y2, v2, and t2, and finally y3, v3, and t3. All right, so between points 1 and 2, the acceleration of Batman is upwards in order for him to launch, but between points 2 and 3, the feet are no longer in contact with the ground, so Batman is influenced only by gravity, and so the magnitude, at least of that acceleration, is the acceleration due to gravity. All right, so we can go ahead and make our table of what we know in order to do the motion part of the problem. So we'll start out with the value of y1 equals 0, v1 equals 0, because Batman starts from rest. We'll set t1 equal to 0. All right, the value of y2 is equal to the 0.2 meters that's given in the problem. So that's how far Batman's center of mass rises during the launching part of this problem. And then the value of y3 is given to be 10 meters. That's quite a jump. That's 30 feet. So the kryptonite must be working well. All right, we can put the acceleration due to gravity, its approximate value of 10 meters per second squared. And basically what I would like to find from this first part of the problem is the value of a sub 1. What is the acceleration during the launching phase? So my strategy for solving this problem is to use the points 2 going to 3 and to try to use the information that's given to find the speed of Batman when he leaves the ground. And then we can work from points 1 to 2, since then we would know Batman's final velocity to find out what the acceleration was during that part of the motion. And for both of these parts, we don't know really any information about the time, so we need to use the velocity, the position, and the acceleration to solve the problem. And so that's going to be the third kinematic equation on the list, actually for both parts. So let's work from parts 2 to 3 first of all. So we would say that v3 squared equals v2 squared plus 2 times a2 times y3 minus y2. And v2 is going to be our unknown. So the final value of the velocity at the top of the flight is 0, so that gets squared, equals v2 squared plus 2 times negative 10 will be our acceleration due to gravity in this coordinate system because we picked positive to be up. And y3 minus y2 will be the 10 meters minus the 0.2 meters that Batman's center of mass started at before the flight. Alright, so we'll have v2 squared equals, multiply the numbers by minus 1, so I'm going to have 20 times 9.8, so v2 will be equal to plus or minus the square root of 20 times 9.8, which equals 196, and the square root of 196 is equal to 14. So v2 is either equal to positive or negative 14 meters per second, and in our coordinate system that we picked, positive is up. We need Batman's velocity to point upwards, so we need to pick the positive root, 14 meters per second. Alright, so now that we've got that, we can go ahead and figure out what the acceleration is during the first part of the motion using the kinematic equations again. So we'll go from point 1 to point 2, and we don't know anything about the time, so we'll need to use the same equation that has the squares in it. So v2 squared will be equal to v1 squared plus 2 times a1 now times y2 minus y1. So this time the acceleration number 1 is our unknown, so we'll put in the numbers. v2 was 14, we'll square that. v1 was 0 plus 2 times a1 times y2 minus y1 is 0.20 meters. So 14 squared is 196, and then I divide by 2 times 0.2, which is 0.4, and that is going to be equal to a1. So therefore the acceleration divided by 0.4 will be equal to 490 meters per second squared. Now that seems like an amazingly large acceleration, and it is. But Batman, as I already commented before, must be superhuman because he's jumping 10 meters into the air, which is 30 feet. So that's the top of a third-story building. So that's a little more than most of us can do. Alright, so we'll go ahead and move on to the next part of the problem then, dealing with the forces now that we have this acceleration. Alright, so we're making great progress on this problem. We did the motion part of the problem that involved 2 steps, and we figured out what acceleration was required by Batman to have while he was pushing off of the ground so he could rise 10 meters up into the air. And it turned out to be this extremely large acceleration of 490 meters per second squared. And so now we can go ahead and do the forces part of the problem. Forces second, and we'll use the forces part of the problem to figure out what was the pushing force that was necessary for Batman to acquire this specific acceleration. So in order to do that, we'll have to draw a force diagram for Batman when he is in contact with the ground. So we'll let Batman be represented by that box, and Batman has two forces acting on him. So one is weight, because he's made of atoms, and the second is this pushing force that actually I'm going to label as P instead of F's of P, and that it includes the effect of the normal force, because that's the force that the floor is exerting on Batman, so Batman has to exert the same force on the floor. Alright, so the direction of Batman's acceleration is upwards. We've already established that. Let's pick a coordinate system to do the force problem where the positive y direction is up. So this is a one-dimensional problem only involving y direction. So we use Newton's second law. And that would tell us that the acceleration in the y direction would equal the net force in the y direction divided by the mass. So putting in the particulars for our problem, we would have plus a1, because Batman's acceleration is up, is equal to the quantity p minus mg divided by m. And now if I solve that expression for the pushing force, I would get m times a1 plus m times g equals the pushing force. So plugging in the numbers, P would be, actually I can factor out an m and get a1 plus g. So the mass of Batman was 80 kilograms. A1 was equal to 490 meters per second squared. G is approximately equal to 10. So we have 80 times 500, and 8 times 5 is 40 with 3 more zeros. So that gives us 40,000 newtons. So this pushing force that Batman has to use in order to launch himself off the ground with this tremendously large acceleration is equal to an exceedingly large pushing force also, 40,000 newtons. That's quite astronomical. Alright, so I have my units. Just to bring the problem to a conclusion, my significant figures, I definitely don't have too many. I think that we have exactly the right amount. Alright, so again, this was a force and motion problem, but we had to do the motion part first, breaking it up into two parts. That helped us find the acceleration that we needed in order to do the forces part of the problem, that then led us to the final target that was Batman's pushing force.